Welcome. In this video we start section 2.2, Proofs about Numbers. There will be 2 videos on this section. In this video we will cover divisibility, rational numbers, and proving by cases. Here's a definition to start us off. We say that an integer a is divisible by an integer b if a equals bq for some integer q. We've seen this divisibility definition before in terms of other numbers. For example, I think we say that an integer a is divisible by 3 if a equals 3q for some integer q. Here's another example. 63 is divisible by 7 because 63 equals 7 times 9. 63 is the a, 7 was the b, and I could write a equals bq. And it didn't really matter what the q was, just so long as some integer exists. How about these next 3 statements? 164 is divisible by 2 since 164 equals 2 times 82. 0 is divisible by 37 since 0 equals 37 times 0. 20 is not divisible by 3 because there is no integer q such that 20 equals 3q. Some vocabulary. We also use the word divides often. We might say 7 divides 63, or 2 divides 164, or 37 divides 0. Here's a sample proof that uses the divisibility definition. Claim: if m and n are divisible by 7, then 3m plus 2n is also divisible by 7. So in our proof we say let m and n divisible by 7 be given. It's a good start. We define our variables and make sure the hypothesis is satisfied. And then use the definition of divisibility. M equals 7t and n equals 7u for some integers t and u. So I'm looking at my conclusion and I want to say something significant about 3m plus 2n. So 3m plus 2n equals, now substitute for m, substitute for n, the 7t and the 7u, do some simplification, and I end up with 7 times 3t plus 2u. Well, since 3t plus 2u is an integer, this shows that 3m plus 2n is divisible by 7. And again, incidentally, we use the closure properties of integers. Now you prove that if 6 divides n, then 9 divides n squared. Pause the video, write out your proof, and then unpause when you are ready to check your answer. Okay, here's a proof that I wrote up for this thing, and so hopefully yours is a little bit similar. Check your work there. Moving on. 2. Rational numbers. Here's our definition for rational numbers. A real number r is rational if there are integers n and d, with d not 0, such that r equals n divided by d. For example, 2.5 is rational since 2.5 equals 5 over 2. I really have expressed 2.5 as a ratio of integers. Negative 3 is rational since negative 3 equals negative 3 divided by 1. And 0 is rational since 0 equals 0 divided by 1. Note, not every number in the world is rational. There are real numbers that are not rational. For example, the square root of 2 is not rational. No matter how you try, you will never, ever, ever be able to express the square root of 2 as a ratio a over b, where a and b are integers. We will prove that a little bit later on in this course. Here's a claim. If x and y are rational numbers, then x minus y is a rational number. How would the proof of this go? Let x and y be rational numbers. That is, x equals a over b and y equals c over d for some integers a, b, c, d, with b and d not 0. There is the direct application of the definition of rational numbers. And now, let's look to our conclusion and write an expression for x minus y. So x minus y equals a over b minus c over d. Simplify that. with a common denominator, put it all together, and now with closure I have that my numerator is an integer, my denominator is an integer, and importantly the denominator is not 0. Since AD minus BC and BD are both integers and that denominator is not 0, this shows that x minus y is rational. Here is a proof for you to try. Prove that if x and y are rational numbers, then the average of x and y is a rational number. Pause the video, write out your proof, and then unpause when you want to check your answer. Alright, here's what I have. Let x and y be rational. I write x as a over b and y as c over d for integers a, b, c, d, and b and d are not 0. Then the average of x and y is x plus y over 2, and that simplifies all the way at the end to AD plus BC divided by 2BD. Since the numerator and denominator are integers, and that denominator is not 0, the average of x and y is rational. Often, when we prove claims, we have to include several cases in our proof. Here's a nice example. This claim says that for any integer n, n squared plus n is even. So to begin the proof, let integer n be given. Either n is even or n is odd. So let's try those two cases separately and see if the result of the claim comes out in both cases. So case 1, suppose n is even. Then n equals 2m for some integer m. Then n squared plus n equals, I substitute the 2m for n, do some algebra, and at the end we end up with 2 times an integer. Since the 2m squared plus m is an integer, then n squared plus n is even. What about the other case? Case 2, suppose n is odd. Oh, and by the way, this suppose is often a good way to begin your cases. We're imagining one situation, and then we imagine a different situation. Case 2, suppose n is odd, then n equals 2m plus 1 for some integer m, applying the definition of odd. Then n squared plus n equals, I'll skip the algebra, and at the end we end up with 2 times 2m squared plus 3m plus 1. Since 2m squared plus 3m plus 1 is an integer, n squared plus n is even. So, for any integer n, n squared plus n is even. Let's see if you can do a proof by cases in this example. Here's our claim. If n is not a multiple of 3, then n squared has the form 3q plus 1 for some integer q. Give it a try, pause the video, and then start up again when you are ready to check your answer. Alright, so before we dive into the proof, let's think about the cases that we will need. We're given that n is not a multiple of 3, so what could it look like? Well, let me write out some integers. And I'll circle the multiples of 3. So my n has to be something like 1 or 2 or 4 or 5 or 7 or 8 or 10 or 11 and so on. Now notice that the number 1 is 1 more than a multiple of 3, and 4 is 1 more than a multiple of 3. 7 is 1 more than a multiple of 3. 10 is 1 more than a multiple of 3. And the 2 is 2 more than a multiple of 3. 5 is 2 more than a multiple of 3, and so on. So basically, the two cases are that this n can be either 1 more than a multiple of 3, or n is 2 more than a multiple of 3. So let n, not a multiple of 3, be given. Then n equals 3k plus 1, or n equals 3k plus 2 for some integer k. That is, n is either 1 more than a multiple of 3, or n is 2 more than a multiple of 3. Okay, first case. Case 1, suppose n equals 3k plus 1. Then n squared equals 3k plus 1 squared, and I expand that using algebra. Case 2, suppose n equals 3k plus 2. then n squared equals 3k plus 2 squared, and I can expand that using algebra. In both cases, look at this, I end up with 3 times something plus 1, where that something is an integer. In either case, we find that n squared has the form 3q plus 1 for some integer q. A last example, we have time for this. Prove that every perfect square is either of the form 4q or 4q plus 1 for some integer q. Once again, for the last time, pause the video, really give this a try, and then start the video again when you are ready to see the answer. Here we go. Proof. Let n be a perfect square. Then n equals m squared for some integer m. Case 1, m is even. Then m equals 2k for some integer k. Then n equals m squared equals 2k squared equals 4 times k squared. That's a good position to be in because remember, one of the outcomes I wanted was that my perfect square was of the form 4q, so that looks pretty good. Case 2. What if m is odd? Now, notice I don't actually use the word suppose here, but that's okay. M is even, m is odd. In this case, m equals 2k plus 1 for some integer k. I will square that, and we end up with 4 times k squared plus k plus 1. So look at the two cases where I ended up. In either case, n has the form 4q or 4q plus 1 for some integer q. This is kind of a funny example because my conclusion is an or statement, and it's true. In the first case, I ended up with a number of the form 4q or 4q plus 1, and in the second case, I ended up with a number of the form 4q or 4q plus 1. Alright, that is where I will stop for this video, and we will do more proof, and we will always do more proofs in the future.